Welcome to the deep dive. Today, we're going to be tackling something pretty fundamental to AI, um, probability theory.
Yeah.
You've sent over a chapter from the deep learning textbook,
Right.
and I'm excited to kind of explore it with you.
Absolutely. This is a fun one. So let's just start with the big picture here.
Yeah.
Why does probability matter so much in machine learning?
Right.
I mean, isn't software development, usually about like writing code that does predictable things?
That's true for traditional software development.
Right.
But machine learning is all about dealing with uncertainty.
Okay.
In fact, you could almost say that probability is like the language of machine learning.
That's an interesting way to put it.
Yeah.
So can you kind of unpack that a little bit more for me? What are the sources of this uncertainty that we need to deal with?
Well, sometimes the uncertainty is just inherent in the problem itself,
Okay.
like in quantum mechanics, where things happen probabilistically.
There's also the issue of incomplete observability.
Yeah.
It's like a game show,
Uh-huh.
There's a prize behind one of the doors, but you don't know which one.
Right.
Your knowledge is incomplete.
Yeah.
And finally, we often have to make, like, simplifying assumptions when we're modeling really complex systems.
Oh, okay.
And these assumptions introduce uncertainty because they don't capture the full complexity of reality.
So it's like we're always working with this like incomplete information or simplified models,
Exactly.
which means we need some way to kind of like
Right.
quantify and reason about the uncertainty that comes with that.
Exactly. And that's where probability comes in.
Okay.
It gives us the tools to say, we may not know for sure, but here's how likely it is that this particular thing will happen.
Okay, that makes sense.
Yeah.
So before we dive into the specifics of the chapter, let's do a quick recap of some probability basics.
Sure. Let's start with random variables.
Okay.
These are essentially variables that can take on different values. With some probability,
Right.
we can have discrete random variables,
Right.
like the outcome of flipping a coin heads or tails,
Oh.
or continuous ones like a person's height or weight, which can theoretically take on any value within a range.
Right. It's like discrete is like steps and continuous is like a smooth.
Yeah, exactly.
Okay.
Now, each random variable has a probability distribution associated with it,
Okay.
which tells us how likely each value is.
Right.
We use probability mass functions for discrete variables
Okay.
and probability density functions for continuous ones.
I remember struggling with density functions in college.
Yeah.
It's not as straightforward as just looking up the probability of a specific value, is it?
No, it's not.
Okay.
The density function tells you the relative likelihood of values
Okay.
within a certain range.
Right.
You actually need to integrate the function over a specific interval to find the probability of observing a value within that interval.
So it's like the area under the curve that matters, not the height of the curve at a single point.
Precisely. Now, there are some probability distributions that are especially important in machine learning.
Yeah.
They're like the building blocks we use to model different kinds of data and make predictions.
Okay, let's talk about some of those all-star distributions. I'm ready for some aha moments here.
Okay, well, a simple one to start with is the Bernoulli distribution.
Okay.
It models events with two possible outcomes, like a coin flip.
Right.
It's determined by a single parameter, usually p, that represents the probability of one of those outcomes,
Right.
say heads.
So if I had a slightly weighted coin that lands on heads 60% of the time, I could model that with a Bernoulli distribution,
Exactly.
where p is 0.6.
Exactly. Now, if we have more than two categories, like rolling a six-sided die,
Right.
we can use the Multinulli distribution.
Okay.
It's worth noting that the term multinulli is relatively new
Okay.
and distinguishes this from the more commonly known multinomial distribution.
Wait, what's the difference? They sound really similar.
The multinulli is for a single trial with multiple outcomes,
Okay.
while the multinomial generalizes that to multiple trials.
Okay.
Think of flipping a coin once versus flipping it 10 times and counting how many heads and tails you get.
Ah, okay. So multinulli is like a snapshot and multinomial is like a movie.
That's a great analogy.
Okay.
Now, probably the most famous distribution is the Gaussian,
Right.
also known as the normal distribution.
Right.
It's that classic bell curve shape,
Yeah.
and it shows up everywhere, not just in machine learning.
Why is the Gaussian so popular? I mean, is that just a coincidence or is there something deeper going on?
There's a fundamental reason. The central limit theorem.
Okay.
It basically says that if you take a bunch of independent random variables and add them up,
Okay.
the sum pends toward a normal distribution, regardless of what the individual distributions look like.
Oh, wow.
Yeah.
So even if the underlying variables aren't normally distributed,
Right.
their combined effect often is.
Often is, yeah.
That's wild. It makes you wonder if there are other, like, hidden Gaussian distributions out there just waiting to be discovered.
It certainly does. Now, similar to the Gaussian, but with a sharper peak, we have the Laplace distribution.
Okay.
It's often used when you want to place more emphasis on a specific point or when you're dealing with data that might have outliers.
Okay, so it's like a more focused bell curve.
Yeah, think of it like this.
Right.
Imagine you're building a model to predict house prices.
Okay.
The Gaussian distribution might assume that prices are spread out somewhat evenly around the average.
Okay.
But the Laplace distribution could capture the fact that most houses are clustered around a particular price point with fewer outliers at the very high or very low end.
So it's a way to make the model less sensitive to extreme value.
Exactly.
Okay.
And finally, let's touch on the Dirac delta distribution.
Okay.
It's not a true function in the traditional sense,
Okay.
but more of a mathematical tool.
Right.
It's like an infinitely tall and narrow spike located at a specific point. It's useful for defining empirical distributions based on observed data.
I'm trying to picture that in my head.
Yeah.
It sounds like a way to pinpoint exact values within a continuous space.
Exactly. For example, if you have a data set of heights,
Yeah.
you can represent it as a probability distribution
Yeah.
where each unique height gets a spike of probability mass using the Dirac delta.
Okay.
It's a way to represent discrete data within the framework of continuous distributions.
Okay, I think I'm starting to get the hang of these different distributions.
Okay.
Like, we have all these tools in our probability toolkit,
Yeah.
and we need to choose the right one based on the kind of data we're dealing with and the problem we're trying to solve.
You got it. And understanding these distributions is just the first step.
Okay.
We also need to think about how to quantify the amount of uncertainty
Right.
or surprise that these distributions represent.
Okay.
That's where information theory comes in.
All right, let's jump into that. I'm ready to see how information theory connects to all of this.
Okay, let's do it.
So you've got these probability distributions, right? Like different buckets holding the likelihood of different events.
Okay, yeah.
Information theory comes in and says, okay, how much stuff is actually in those buckets?
Right.
How unpredictable are things?
So how do we measure that, like, stuff? How do
Yeah.
we measure that unpredictability?
Yeah, so the basic unit is what's called self-information.
Okay.
It tells us how surprising a specific event is.
Okay.
The less likely something is, the more self-information it carries.
So if I told you I had cereal for breakfast, that wouldn't be very informative.
Right, right.
But if I told you I won the lottery.
Exactly.
Yeah.
That would be much more surprising, hence more informative.
Okay.
Now, to get a sense of the overall surprise level of a whole distribution,
Right.
we use what's called Shannon entropy.
Entropy, that sounds familiar from
Yeah.
like physics or something.
It
It is.
isn't related.
Yeah. In physics, entropy is about disorder.
Right.
And here it's about how unpredictable a distribution is.
Yeah.
High entropy means things are all over the place.
Right.
Low entropy means it's pretty predictable what you'll get.
Okay.
So a coin flip has more entropy than, say, a weighted die that almost always lands on 6.
Right, right. Okay. Yeah, that makes sense.
So now why is this important for machine learning?
Yeah, why?
Well, let's imagine you're building a system to classify images of cats and dogs.
Okay.
If your data set has high entropy, lots of variety in the cat and dog pictures,
Okay.
your model needs to be more complex to handle all that variation.
So the entropy kind of like helps us gauge the difficulty of the learning tasks, like
Yeah.
how much figuring out the model has to do.
You got it. High entropy data set is like a messy room.
Right.
It takes more effort to organize.
Right. Okay.
Now, there's another concept called KL divergence,
Okay.
which helps us compare two different probability distributions.
So it's like measuring how different those buckets of likelihood are from each other.
That's the gist, yeah. But here's the tricky part.
Okay.
KL divergence isn't symmetrical. The divergence from distribution A to B isn't necessarily the same as from B to A.
Huh. That's kind of counterintuitive.
Right,
Can you give an example of why that matters? I mean, it sounds pretty abstract.
yeah. So imagine you have two mountains,
Okay.
one with a single peak and another with two peaks.
Okay.
If you start at the single peak and you measure the effort to climb to the double peak mountain,
Right.
it's different from the effort of starting at one of the double peaks and going to the single peak.
So the starting point matters
Yes.
for how we measure the distance between them.
Exactly.
Okay.
So how does this apply to machine learning?
Yeah.
Well, in model training, we often use KL divergence to see how different the model's predicted distribution is from the actual data distribution.
Okay.
We want them to be as close as possible.
So we're like nudging the model's bucket to
Right.
match the shape of the real data bucket.
Exactly. The lower the KL divergence, the better the model is at capturing the true patterns in the data.
This is making me realize that like probability and information theory aren't just like abstract math.
No.
They're like the backbone of how these AI models learn and make decisions.
They really are.
Yeah.
And to handle the complexity of these models, especially when we have lots of variables interacting,
Yeah.
we often use visual tools called graphical models.
Okay. Graphical models, they sound cool.
Yeah, they're great. They're like maps of probabilistic relationships.
Okay.
You have nodes representing variables and links showing how they depend on each other.
So instead of like this jumbled mess of formulas,
Right.
we get a clear visual picture.
Precisely. And there are different types of graphical models.
Okay.
You've got directed models, also called Bayesian networks.
Okay.
Use arrows to indicate causal relationships.
So if variable A influences variable B, we draw an arrow from A to B.
Yes. And this implies conditional dependence. The probability of B depends on the value of A.
Got it.
Then we have undirected models, or Markov random fields, which just show connections without specifying a cause and effect direction.
So it's more like saying these two variables are related,
Yes.
but we're not saying which one comes first.
Exactly. The power of graphical models comes from their ability to encode what are called conditional independence assumptions.
Okay.
This means that knowing the value of one variable might tell us that two others are independent,
Mhm.
even if they initially seemed connected.
Okay, I'm a little lost there. Can
Yeah.
you give me like a concrete example?
Sure. Let's say we have a model for predicting whether someone will go for a run.
Okay.
We have variables for the weather,
Okay.
their motivation level, and whether their friend is joining them.
Okay. I can see how those might all be related.
Now, if we know that the person is highly motivated,
Right.
the weather might not matter as much for predicting if they'll run.
Okay.
Their motivation essentially blocks the influence of the weather
Okay.
in this specific scenario.
So knowing they're motivated makes the weather and running conditionally independent.
Exactly. And this kind of reasoning allows us to simplify complex probability distributions.
Okay.
Instead of calculating the probability of every possible combination of variables,
Right.
we can break it down into smaller chunks
Yeah.
based on these conditional dependencies.
It's like simplifying a huge math problem by factoring out common terms.
That's a great analogy. And the efficiency is why graphical models are so valuable in machine learning.
Okay.
They help us manage complexity, understand relationships, and even design better models.
This is all incredibly insightful.
Good. I'm glad.
I'm starting to see how these concepts from probability distributions to information theory and graphical models are all interconnected and crucial for building intelligence systems.
They are.
But we've covered a lot of ground here. I think it's time to take a break and let our listener digest all this amazing information. We'll be back soon to explore how these ideas play out in real-world machine learning applications. Okay, so we're back. And ready to kind of like see how these theoretical ideas we've been discussing actually translate into like, real world machine learning.
Let's jump right in. One of the most common tasks in machine learning is classification,
Okay.
figuring out which category something belongs to.
Right.
Think about filtering spam emails
Right.
or recognizing different objects in an image.
Yeah, I can see how those would be like classic examples.
Yeah.
So how does probability fit into that picture?
Well, at its heart, a classifier needs to estimate the probability that a given input,
Yeah.
an email, an image, whatever,
Right.
belongs to a certain category.
Right.
It does this by learning from a bunch of labeled examples,
Okay.
like emails that have already been marked as spam or not spam.
So it's like the classifier is building up a sense of what spam looks like
Exactly.
based on the patterns it sees in the data.
Exactly. And it uses those patterns to calculate the probability that a new unseen email is spam.
Okay.
For example, the classifier might learn that emails containing certain words, like free or prize, are more likely to be spam.
So it's not just looking for specific words,
Right.
but also learning how those words affect the overall probability of an email being spam.
That's right. And the type of probability distribution we use to model this can vary depending on the kind of data we have.
Right.
For example, if we're looking at word frequencies in emails,
Okay.
a multinomial distribution might be a good choice.
Okay.
But if we're looking at something like the length of an email,
Right.
a Gaussian distribution might be more appropriate.
So it's like choosing the right tool from our probability toolkit, just like we talked about earlier.
Precisely. And once the classifier has learned these probabilistic relationships,
Right.
it can use them to make predictions about new data.
Okay.
It's essentially making informed guesses based on the patterns it's seen before.
And I guess those guesses are expressed as probabilities. Like there's an 80% chance this email is spam.
Exactly. And this probabilistic approach allows us to deal with the uncertainty that's inherent in many real-world problems.
Okay.
There's rarely a way to be 100% certain,
Right.
so we rely on probabilities to guide our decisions.
Okay. That makes sense for classification.
Right.
What about other types of machine learning tasks?
Yeah.
Like regression, where you're trying to predict a continuous value
Yeah.
instead of a category.
Probability plays a huge role in regression, too.
Okay.
Think about predicting the price of a house based on its features.
Okay.
The model might learn a probability distribution over possible prices given those features.
So instead of just spitting out a single price,
Right.
it's giving you a range of possible prices
Exactly.
with associated probabilities.
You got it. And that's super valuable because it gives you a sense of how confident the model is in its prediction.
Right. So it might say something like there's a 90% chance the house is worth between $450,000 and $500,000.
Exactly. And that level of uncertainty is crucial for making informed decisions.
Right.
You wouldn't want to buy or sell a house based on a single price point without knowing how much uncertainty surrounds that estimate.
This really highlights how thinking probabilistically adds a whole new layer of sophistication to machine learning.
Absolutely. Now, let's zoom back out to the bigger picture.
Okay.
Remember those information theory concepts we talked about?
Mm,
Entropy and KL divergence.
yeah. Those were pretty mind-bending. How do they actually play out in model training?
Well, one way to think about model training is that we're trying to minimize the surprise or uncertainty
Okay.
in the model's predictions.
Okay.
We want the model to make predictions that are as certain and accurate as possible.
So we're basically trying to reduce the entropy of
Yeah.
the prediction errors.
Exactly. We want the model to be as deterministic as possible, given the data we have. And KL divergence comes into play because we often use it as a loss function during training.
Right.
It helps us measure how different the model's predicted probability distribution is from the true distribution of the data.
So we're trying to nudge the model's predictions to match the reality of the data as closely as possible.
Exactly. And as we minimize that KL divergence, the model gets better and better at capturing the underlying patterns in the data.
This is really giving me a deeper appreciation for how probability and information theory are intertwined with the very process of learning.
Right.
It's like we're shaping these models by
Yeah.
guiding them towards less uncertainty and more accurate predictions.
That's a great way to think about it.
Yeah.
And to help us visualize and manage all this complexity, especially when we're dealing with lots of variables,
Yeah.
we often turn to graphical models.
Right. Graphical models.
Yeah.
I'm eager to hear more about how they come into play. It's like
Oh.
we've been building up to this from the basic building blocks of probability
Right.
to the intricate world of model training. And now we have these visual tools to help us navigate it all.
They're incredibly valuable.
Yeah.
Especially as models become more sophisticated and data sets become more complex.
Right.
Graphical models help us make sense of the chaos
Okay.
by providing a visual representation of how different variables depend on each other.
So it's like creating a roadmap of the relationships within the model.
Exactly.
So we don't get lost in a maze of equations.
Exactly. And that visual representation is incredibly helpful for understanding how information flows through the model,
Right.
identifying potential bottlenecks,
Okay.
and even debugging issues.
It sounds like they're not just helpful for understanding existing models,
Right.
but also for designing new ones.
Absolutely. By starting with a graphical model, we can systematically incorporate our prior knowledge and assumptions about how the variables relate to each other.
Right.
It's like having a blueprint that guides the construction process,
Yeah.
ensuring that the model is well-structured and interpretable.
Wow. So graphical models are like the ultimate tool for taming the complexity of these powerful AI systems.
They really are.
It feels like we've come full circle.
We have.
From understanding the fundamental role of probability to seeing how these ideas are shaping the future of AI development.
It's been a fascinating journey, and I think the key takeaway here is that probability isn't just some abstract mathematical concept.
Hmm.
It's the language of uncertainty.
Yeah.
And it's essential for building AI systems that can learn, adapt, and make informed decisions in the real world.
This has been an incredible deep dive. We've covered so much ground, from the basics of probability distributions to the nuanced insights of information theory and the visual power of graphical models.
Yeah, we did.
I feel like our listener is now equipped to not only understand the technical foundations of AI, but also to appreciate its incredible potential and the challenges that come with it.
Absolutely.
And one final thought for you to ponder as you continue your exploration of this amazing field. If probability is the key to understanding and navigating uncertainty, how can we use this knowledge to build AI systems that are not just powerful,
Right.
but also responsible, ethical, and beneficial to humanity? That's something to think about as we venture further into the age of intelligent machines. Until next time on The Deep Dive.